Hello, people. Here we are, ready for our first lecture of exam 2. And a lot of people still have not taken exam 1, so I'm going to take it a little bit easy on you today. By the way, I don't know if you saw the latest announcement, but I delayed I extended the deadline for the exam to Friday at 4. A lot of people are struggling with getting respondents to work. Seems like all of those people are Mac people, unfortunately. One person told me that Isabella, she should be here soon. She told me that what did she say? She emptied her disk space, freeing up storage, and then it seemed to work. So maybe that can help for some of the rest of you. Free up storage in your hard disk, and it may work better. I don't know. I'm not an expert at that. Okay. Matt and David, should we go ahead and do it? Oh, here's Che. Welcome, Che. Is it Shay? Okay. So Matt cannot talk to me today. Camera and microphone are not working, but we, Zoe, Hannah, and I, can hear you and we're following along. Okay, good. Good to know. Nothing worse than giving a lecture in an empty room. Glad to know someone's listening. All right, so why don't we go ahead and get started here? It's going to be a short lecture because, like I say, we're right in the middle of an exam already. But we'll go ahead and do a lecture because that's why we're here. Oh, and by the way, quick announcement before I move on, no quiz this weekend. Okay, I like to do a quiz every weekend, but I mean, there's not that much material, A, and B, some of you guys are still stressing over the test, so we're not gonna have a quiz this weekend. I will start with what? Oh, come on, man. Why is it doing this? Chrome tab. Oh, man. So it's not giving me the option of opening my PowerPoint for some reason. Boy, I really, really like this Teams. They've done a lot to make it harder for us. All right, we're just looking at Chrome. We can't do that. Oh, for the love of God. Chapter 8. There we are. Chapter 8. Oops. Okay, so here's another innovation. Dr. Lounsbury told me some people were wondering if I could put my notes here. So what I've been doing is I'm still doing notes in Microsoft Word, but I'm copying them and pasting them on the slides that they pertain to. So if you want to look at it that way, then that's available for you now too. And so chapter 8 is general modes of intercellular sharing. Signaling, I'm sorry. Signaling. Sorry, I'm still getting myself together here. Okay, so can anyone tell me, do you see slide 2? Ligands and receptors? Yes, okay. So what this chapter is about is everything that happens outside of the cell. It's also putting a lot of internal signal transduction stuff into it. The way they seem to have separated these two chapters is chapter 8 is ligands and receptors, and chapter 9 then is signal transduction. But they kind of mess the two together from time to time. I'm gonna follow the book, the order of the book for most things, just so that you've got that reference to go with it as well. But I got to be honest with you, as a pharmacologist, I love this stuff. This is my bread and butter here. So I'm probably going to go off on tangents and explain things that you don't want to know about, but I enjoy anyway, sorry. But anyway, ligands and receptors. So ligands are basically signaling molecules. The term ligand means something that sticks, right? If you ligate things together, a ligature, stuff like that, sticking. So a ligand is a molecule that's going to stick to a receptor. And it has to do with, you know, the functional side groups on the amino acids of the receptor matching perfectly with the side groups on the ligand, whether it's, well, we'll talk about what ligands are in a sec. But anyway, we've got 3 different types of ligands that we want to talk about. You've got small molecules, proteins, and hydrophobic molecules, which are also small molecules. So your small molecules, like neurotransmitters, are always small, or almost always small molecules. Never in biology say always. Never say always, even because there's always exceptions. I just said always. Oh well. Small molecules, things like epinephrine and histamine. So these small molecules are typically or often metabolized from amino acids, so they tend to be amines. Like histamine is made from a simple decarboxylation of histidine. Epinephrine is made from tyrosine. So basically tyrosine is converted into L-DOPA, which is converted into dopamine, which is converted into norepinephrine, which is then converted into epinephrine. So you've got, you know, 2 neurotransmitters there, dopamine and norepinephrine, and a hormone, epinephrine, all from that same pathway. By the way, your book calls epinephrine a neurotransmitter. I don't know of any examples of it being used as a neurotransmitter. It's pretty much always a hormone, endocrine hormone. Norepinephrine is the neurotransmitter. So anyway, I find that annoying, but it is what it is. So small molecules, and we'll talk about a bunch of them in this chapter. Then you've got proteins. I think the biggest protein hormone is prolactin. It's pretty big. Insulin is another one. Endorphins, vasoactive intestinal peptide. I mean, you've got a lot of different protein molecules that are used as ligands. I think the smallest one might be about 3 amino acids put together. So they can go as small as just a small peptide, or as big as something like prolactin. You can see how big that is with 4 or 5 alpha helices. And then we've got hydrophobic molecules, and they mainly come down to 3 different hydrophobic molecules. You've got your steroids, which are cholesterol based, thyroxine, thyroid hormones, and then you've got your retinoid hydrophobic hormone. So we'll talk about each of those separately as we go through today. So these are the main types of things we have as ligands. In terms of receptors, we've got cell surface receptors, which are mostly covered in chapter 9. So we'll go into detail of those in chapter 9. And then intracellular receptors, which we'll talk about some of them today. And the intracellular receptors are for the lipophilic hormones, or the hydrophobic lipophilic hormones, because they will diffuse right through the cell wall and into the cell. So the receptors are internal. All your other ligands are going to be hydrophilic, and they can't get into the cell. So you've got cell surface receptors there to respond to them. Okay, so in terms of hormonal release, we've got 4 different mechanisms of hormonal release. Usually when we think of hormones, we think of endocrine hormones, where you've got a gland somewhere, like your adrenal medulla, right? Which is in the adrenal glands on top of the kidneys. And that will then spill a hormone out into the extracellular fluid, like epinephrine spilled into there, and then that gets taken up in the bloodstream and then gets distributed to all cells of the body. And then the only cells then that are going to respond to it are going to be cells that have receptors for that hormone. So certain target cells have got those receptors, and they're going to respond to the hormone. That's your endocrine system. And then you've got paracrine, which is when one cell releases something directly onto another cell and that second cell responds. We'll see this in the next chapter when we talk about growth factors, where you've got cells that will release a growth factor into an area. Oh, we talked about this, that's right, in chapter 3 with chemotaxis, where you've got like a platelet releasing platelet-derived growth factor, and then all the cells in the area will respond to that growth factor. And also cells like fibroblasts will release fibroblast growth factor, and they will, other cells in the area will respond, but also the fibroblasts themselves will respond by going into mitosis and making more fibroblasts. So that's called autocrine, when a cell releases a hormone and responds to it itself. So that's endocrine, paracrine, and autocrine. Those are 3 different types of hormone release. Now, the third one isn't really release, but it's another hormonal type thing. This is one of my favorite examples of juxtacrine signaling, which is the Notch pathway. We'll talk about this in chapter 9. But the thing about juxtacrine is basically you've got 2 cells right next to each other. And the cell with the, if you can see me, I'm doing air quotes, cell with the hormone on it. The hormone here in this case is delta, but it's a transmembrane protein. So it is attached to the membrane. It's not being released, it's just being held there in the membrane. And then the other cells got the receptor. So Notch here is the receptor. So these 2 cells come in contact with each other, and when they do, they bind to each other, and that activates signal transduction that changes transcription. So that's juxtacrine, when 2 cells touch each other, and then you get signal transduction between them. Another really good example of this is like cytotoxic T cells will be expressing the protein Fas ligand, and cells that need to undergo apoptosis will express Fas. And when the cytotoxic T cell sees that, it activates Fas, which is a receptor that activates apoptosis. That's another example of juxtacrine signaling, and we'll be seeing that later in this class as well. So anyway, endocrine, paracrine, autocrine, and juxtacrine, 4 different ways that hormones can work. Now, on the other side, now, as I said before, the response in the cell depends on if they have the receptor. Number one, if you've got like I don't know, corneal cell in your eye doesn't have beta receptors, so you release epinephrine, they're not going to respond to it. You have to have a receptor to respond. But in addition to just having a receptor or not, it also depends, the response will also depend on which type or subtype of the receptor is there. So now I don't want you to memorize this, but this is just an example of how many different types of receptors there can be. So in terms of adrenoreceptors, which are going to respond to norepinephrine or epinephrine, you've got alpha 1, alpha 2, and beta types of receptors. And each of them are found anatomically in different places, and they will have different responses to the hormone. Alpha 1s tend to be postsynaptic, and on a lot of different cells. And in addition to alpha 1, you've got alpha 1A, B, and D. I imagine there's a C. I don't know why there wouldn't be a C, but you've got 3 different alpha 1 receptors. Alpha 2 tend to be presynaptic receptors. You've got alpha 1A, alpha 2B, alpha 2C, and beta receptors. You've got 3 different beta receptors, beta 1 and beta 2 being the most important ones. So point of this is just that what the response the cell has to the hormone, every cell is going to have its own designed response, and the response then depends on which receptor is there. And you can have many different subtypes of any particular receptor. And again, just to reiterate, don't memorize the slide. I'm just showing the diversity of receptors that can be encountered. Okay, and then on top of that, if you pick out any one of these receptors, each individual type and subtype of receptor can be linked to a different signal transduction pathway. So the example I'm giving you here is M1 receptors. So I probably should have used this as the example on the previous slide. Acetylcholine has got two major different types of receptors. There are nicotinic receptors and muscarinic receptors. Of the muscarinics, there are multiple subtypes of muscarinic. And you've got your M1, your M2, and probably many others. So the M2, so the exact same receptor in two different tissues can be linked to different things. Here you can see M1 is linked to inhibiting the production of cyclic AMP, and it can also be linked to activating a potassium channel. So these are both kind of inhibitory responses. So again, it depends on the physiology of that cell and what, evolutionarily, what was developed for that cell to do when it saw acetylcholine. In the atria, we're inhibiting or increasing potassium leak, which is going to decrease conduction velocity across the atria. It's going to slow things down, decrease contractility. In the SA node, it's going to decrease cyclic AMP, which is going to decrease the heart rate. So different, the same receptor can be linked to different signal transduction pathways, resulting in different responses in different cells. Okay, so that's broad general stuff about hormones and receptors. And now the chapter gets a little more specific. We want to talk about lipophilic hormones first. I always, in my other class in Plattsburgh, I usually talk about lipophilic hormones first because I kind of get them out of the way because they're so simple. Let's just talk about it and get it over with, and then we can move on. Because the mechanisms are so much simpler here for lipophilic hormones than for hydrophilic hormones. But anyway, in terms of lipophilic, we've got 3 different types that your book talks about. So that's what I'll talk about. I think it's possible. Well, no, I think that's about all there are. Well, I don't know. I could be wrong. We're just going to stick to these 3. So anyway, one are your steroids, and your steroids are all based on cholesterol. So basically, organs or glands that are going to release steroids have got cholesterol in them, and they make the hormone as it's needed. So it's not stored in a vesicle like some other hormones will be. We'll see that in chapter 9. It's just made it's made and stored. It's made as it's needed and then released. So in terms of steroids, we've got 2 different types. We've got adrenal cortex hormones. We're going to call those adrenocortical hormones, adrenocorticosteroids. So you've got glucocorticoids and mineralocorticoids. So your glucocorticoids are like cortisol, and cortisol regulates glucose production and basically stress response. So when you're stressed, you release cortisol, and that amps your body up to deal with the stress. Aldosterone, on the other hand, is a mineralocorticoid, and the mineral part of it represents the fact that it's going to control sodium and potassium balance in the kidneys, through the kidneys. So, if your blood pressure drops, you'll release aldosterone, you'll reabsorb more sodium, and then water with the sodium, so your blood volume comes up to bring your blood pressure back up. So aldosterone then is a mineralocorticoid. And then you've got your sex hormones, estradiol, pregnenolone, testosterone, progesterone. Let me look real quick here, my notes. Okay, so basically those are, what you would think of in terms of your sex hormones. They're, establishing secondary sex characteristics, and also regulating the reproductive system. Okay, so those are your steroid hormones. Another type of nonpolar hormone is the retinoic acid. Retinoic acid is made from retinol, which is a vitamin A, basically. And retinol is converted by 2 quick oxidation reactions from retinol to retinal to retinoic acid. And retinoic acid is the hormone. So it's basically regulated by having the enzymes around that are going to convert it, because you've got a certain amount of vitamin A in your body, and if you've got the enzymes up, they convert that retinol into retinoic acid, and then it binds to its receptor, which is in the cytoplasm, and that receptor then goes into the nucleus and activates genes based on binding to sequences there. Talk more about that in a minute. Okay, so retinoic acid basically is made as needed. It is an autocoid type hormone in that the cell makes it and then responds to it. It can also be a paracrine hormone where it's made and then diffuses out of the cell and then activates receptors in neighboring cells. If you've had developmental biology, you've heard of retinoic acid. It's really important in establishing the somites during neurulation. Combination of that and Wnt FGF are going to establish the somites. And so early embryo development, really important things going on here with retinoic acid. And I don't know, you probably know about this, but I always like to throw some more drugs out because drugs are fun. What is it called? Retin A. The drug Retin A is used for people with really serious acne problems, chronic long-term acne problems. Typically a few months on Retin A totally clears it up. But with the drug, if a woman is taking it, they make you be on birth control as well, because this Retin A, because retinoic acid is so important in embryo development. If you're taking Retin A, you're totally going to screw up any kind of embryos that are developing. So very much contraindicated in pregnancy. So anyway, that's retinoic acid. It's made when it's needed and used and binds to internal receptors that then activates transcription. Thyroid hormones. Here's a weird and complicated one. So the thyroid has got these follicles in it, and with an internal a fluid-filled area here. And so the thyroid cell will make a complicated protein here called thyroglobin that's got a lot of tyrosine sticking out. And so that protein then will get exocytosed into that follicle area. And in there, you've got an enzyme that's going to put iodine on the tyrosines of that thyroglobin, and then it will get endocytosed back into a thyroid cell, which will then cleave that off and release it as T3 and T4. So kind of a complicated mechanism of release here for your thyroid hormones. T3 and T4. T4 is the thyroxine. T3 is the one with the more complicated name, triiodothiamine. Okay, so how do these lipophilic hormones work? Two different main ways and two possibilities for the second way. Basically, the receptors, these hormones being lipophilic are going to diffuse right through the cell membrane. So the receptors are internal. Some receptors, like the glucocorticoid receptors, will be in the cytosol. So over here with your glucocorticoids, you've got your glucocorticoid receptor, and you've got three proteins here that are kind of scaffolding it, holding it in place, getting it ready so it's not floating around free. Heat shock protein 70, HSP 90, and immunofilin, I believe. I may have said that wrong. Immunofilin. No, I got it right. So immunofilin, HSP 90, and HP 70 are kind of coordinating this inactive glucocorticoid receptor. When cortisol comes in, it binds to it, and these proteins release it. It then dimerizes and then binds to the DNA. Now, this is a really weird way of looking at DNA. I'm not sure this is correct, but basically this DNA they're showing here is the nucleosome structure. So when DNA is packaged, it winds around histones. So the purple things here, let me see if I can blow this up. The purple things here are histones, or 8 histones and 200 base pairs of DNA around it. So that is your nucleosome structure. Now, I don't know. I tend to disagree with your book on this one, in that this receptor is not going to bind to this DNA when it's wound up with histones. That just doesn't make sense to me anyway. But basically, this receptor is looking for specific base pair regions in the DNA to bind to. So it's only going to bind to the enhancer regions of specific genes, and then it's going to turn those genes on or turn those genes off. So that's what the glucocorticoid receptor is doing. Now, a little bit different, your estrogen receptor, instead of being in the cytoplasm, it's actually in the nucleus. But again, it's being scaffolded here by HSP90. So in the inactive form, HSP90 is binding it. Estrogen diffuses into the nucleus, binds the receptor, and the HSP90 releases the receptor. And again, the receptor dimerizes. Now, what's different here with our estrogen receptor is the receptor is going to bring with it another protein, HAT, histone acetyltransferase. And this is a co-activator. So what's going on with HAT is HAT is going to put acetyl groups on these tails of the histones. And because of that, the histones will let go of the DNA will open up, and then you can get transcription. So this is considered a co-activator because it helps to unwind the DNA. And then once the DNA is unwound, that estrogen receptor will again bind to specific sequences in the DNA, act and turn on specific genes. And then we've got a similar but different thing going on over here with the thyroid receptor. So the thyroid receptor hormones are in the nucleus, instead of in the cytoplasm, but also they're bound to the DNA already. But even though they're bound to the DNA, the gene is still repressed because you've got HDAC on top of it. This is histone deacetylase. So histone deacetylase will take the acetate groups off histones, and that causes the DNA to bind up again to what's the word? I think I just used it a minute ago. But basically, it's compressed, and the base pairs are not accessible, so you can't get transcription. When the thyroid hormone comes in, it binds to the receptor, and the receptor then releases HDAC and picks up HAT like it did over here. And then we acetylate these histones, and the DNA opens up, and then you get transcription. So 3 different types of hormone receptors. You've got your glucocorticoids, which are in the cytoplasm, the estrogen receptors, which are in the nucleus and also have this co-activator, HAT. And then you've got your thyroid hormones that are in the nucleus, bound to the DNA already, and they've got the repressor here, HDAC, which then gets replaced by the activator, HAT, when the hormone is around. Okay. Now, the next part of your book talks about the hypothalamus pituitary axis, the HPA. I don't want to get into it too much. I think it's more physiology than cell biology, so I'm not getting into it. But basically, well, I'm going to talk about it a little bit just because I like talking about it, but it's not important for this class. Basically, your hypothalamus is like the master control gland, and your hypothalamus will release releasing factors that go into a small vein called a small portal vein. So they go straight from your hypothalamus to your pituitary, the anterior pituitary. And the anterior pituitary then releases hormones that go off to the actual gland that's going to secrete the actual hormone, and they cause release of there. So, hormones are released from the hypothalamus, goes to anterior pituitary, anterior pituitary releases a hormone. It goes to the sex cells maybe, and then you get release of estrogen, progesterone, things like that. I don't want to talk about it too much here. I think it's more physiology than cell biology. But moving on, what I do want to talk about histamine. So your book goes into histamine a lot, and I'm not sure where else it would be covered. And I think it's kind of an interesting hormone, paracrine hormone, paracrine autocrine hormone. It's released locally based on cellular responses in the local area. So we've got 4 different histamine receptors. And again, the response to the hormone depends on what receptor is there. So the main ones here that are important are the H1s and H2s. Those are very different receptors. We've got very different drugs for them, and they do totally different things. So your H1 receptors are the ones that are associated with immune response and inflammation and things like that, which we'll talk about in a sec. But basically, your H1 receptors are going to stimulate the breakdown of PIP2 to release IP3 and then calcium release inside the cell. That whole business, PLC through calcium here, we're going to talk about in chapter 9. Let's not stress on it if you don't understand it. If you understand it, good for you. If you don't worry about it. We'll talk about it in the next chapter. But basically, H1 receptors are linked to calcium release inside the cell. And then that activates the cell to do something. And we'll see that in a minute. Okay, so, oh no, I want to talk about it now. So let's see, some of the things that H1 receptors will do is cause smooth muscle cells to contract. So if these H1 receptors are in your bronchi, they'll cause contraction and decrease airflow into your lungs. Bronchoconstriction. They can cause GI cramping. Probably the most well-known response to the average person, though, is in the tissues where you get activation of endothelial cells. And then those endothelial cells will, again, activate phospholipase C, IP3, calcium release, turn on nitric oxide synthase, and make nitric oxide. Nitric oxide we'll talk about in the next chapter. So nitric oxide then will cause relaxation of smooth muscles. It'll make the endothelial cells leaky, and that's going to start that inflammation response, because then you'll the relaxed smooth muscle increases blood flow into the area. The endothelial cells get leaky, so you get fluid into the area, and you're also going to attract immune cells into the area. And of course, if you're overdoing your immune response, you want diphenhydramine, which is Benadryl. I don't know if they still use this clinically. I think they do. I know you can buy it over the counter. Diphenhydramine H1 blocker. It also makes you tired because there are H1 receptors in your brain that are important for stimulation. So you block those, you get tired. I think also diphenhydramine has got anti-muscarinic properties, and that'll also make you tired. So it's kind of a dirty drug. Anyway, one thing that made my life better was when they came out with H2 receptor antagonists. So H2 receptors then are found mainly in the GI tract, and they're going to be linked to inhibiting the production of cyclic AMP. And by doing that, you're releasing more acid into your stomach. So H2 receptors cause an increase in acid production in the stomach. So your antagonist there is omeprazole, which, I mean, I developed an ulcer in grad school. I hope you guys don't. I did. And I struggled with it for years until omeprazole went over the counter, and then my life got instantly better. So this is a really good drug. I'm still on it today. If I don't have one every 12 hours, I get horrible heartburn. So anyway, so I'm addicted to that one. Okay, H3 receptors. These tend to be presynaptic in the central nervous system. So just like I said, you've got H1 receptors in the central nervous system. Those would be postsynaptic. These H3 receptors are presynaptic, and they inhibit the release of histamine in those synapses. That whole process of presynaptic receptors inhibiting release, we're going to talk about at the end of this chapter, so don't stress on it. Just know that the H3s are presynaptic. H4 then, H4 receptors are on mast cells, basophils, and eosinophils. So if we go back to our H1 release, H1 activation. H1 activation causes the leaky endothelial cells, and then the histamine in the area is also going to be recruiting mast cells in that way. And then some of these other immune cells are being recruited to the area through that leakiness of the endothelium, and that's part of your inflammation response. Okay, so we got 4 different receptors. So let's talk about mast cell degranulation. And this is that inflammation response. And in a normal setting, it's a good thing. It activates the cell to get rid of the invader really quickly. In a bad situation, it can go systemic and overreact and cause anaphylactic shock. So this is the mechanism as it works. The first time you're exposed to an antigen, here we're talking about ragweed pollen, your B cell picks it up and it responds to that ragweed by producing IgE. IgE then will bind to IgE receptors on the mast cells. So mast cells have got these Fc epsilon R1 receptors, Fc meaning the constant portion of the antibody. So with your antibody, the kind of the 2 things sticking out on top are variable regions that are going to be specific for the antigen, and then the stalk at the other end is going to be a constant region. So it's going to be the same for all IgEs. So you've got receptors there on the mast cells for that constant region. So then your mast cells get covered in this IgE. Now, the next time you see that allergen, the allergen is going to link to 2 different IgE molecules, and then that's going to cause the receptors there to bind together, and that's going to activate, again, the release of calcium in the cell. And the calcium release then is going to bind to going to do something we've seen before with smooth muscle. Calcium release binding to calmodulin. Calmodulin's then going to activate myosin light chain kinase. In these cells, that activation of the MLCK is going to cause the granules to be released from the cytoskeleton. Now, those granules have got a bunch of histamine in them. They also have some proteases in them and some other chemicals. So it's kind of like this potent cocktail of things to attack the invader. So it's releasing a bunch of histamine to bring more cells into the area, and proteases to break down some of that extracellular matrix so cells can move around in the area easily. And these chemical mediators are causing your characteristic symptoms of allergy. And that's degranulation. So granulation is the granules are basically large vesicles full of histamine and proteases and other things that are going to cause the immune response in that area. Okay, I promised you a short lecture, and I think I want to stop there, but I want to show you a really cool animation I found about this degranulation. So let's stop sharing. And what is this? Nope, don't want you. Okay, hang on, I'm going to bring something up here in a sec. So this video is in your Brightspace. Let me bring it up and then I'll share it. All right, we're going to have to watch a commercial, unfortunately. Share. Come on. Come on, come on, come on, come on, please, please me, oh yeah. I hate the Beatles. Okay.
With the American Airlines Advantage program, earn rewards earlier.
Clever Lab. Mast cells line the tissues exposed to the outside world. They lie under the surface layer of cells in the skin, nasal cavity, stomach, intestines, and lungs. Mast cells also surround blood vessels and nerves. They originate from stem cells in the bone marrow and enter the blood as immature cells. They then migrate to the tissues where they mature into recognizable mast cells. Note that mast cells are distinct from basophils. Each mature mast cell contains hundreds of granules. These granules contain protein and chemical mediators. One role of mast cells is to protect the body from foreign invaders. They protect the body by detecting bacteria, viruses, parasites, venom, or physical harm. This detection is via their cell surface receptors. The most well-known mast cell receptor is the IgE antibody receptor, the Fc epsilon receptor 1. These receptors only exist on mast cells and basophils. The IgE antibody circulates through the body at minute levels. This low level is because the majority is bound to the IgE receptors. Mast cells also have other receptors. They can respond to IgG antibodies and components of bacteria and viruses. Within seconds of receptor binding, they can release their granules. The primary mediators released are histamine, tryptase, chymase, carboxypeptidase A, and heparin. These act on the surrounding tissues. They dilate blood vessels to slow the blood flow, as well as make the blood vessels more sticky for immune cells. These effects attract immune cells into the tissues. They make the blood vessels leaky, which allows antibodies to enter the tissues. The antibodies and immune cells neutralize and remove the infection or toxin. Once removed, mast cells make anti-inflammatory mediators. These stop further immune cells from entering the tissues. They also promote the rebuilding of tissue and removal of dead cells. The tissue returns to normal and the mast cell regranulates to be ready for future infection. But with so many granules ready to release at a moment's notice, it's easy to imagine how things can go wrong. An allergy is an overreaction of the immune system to the environment, and mast cells cause many allergies, such as hay fever, asthma, food allergies, drug allergies, insect stings, and insect bites. Whether you develop any of these depends on both your genetics and the environment. So genetics alone is not enough. You also need exposure to the allergen via a broken barrier in your skin, intestine, or lungs. When allergens make it into the tissues, they activate the immune system. The activated immune system produces antibodies, including IgE. IgE antibodies bind to the IgE receptor on your mast cells and basophils. When you re-encounter the antigen, it binds to the IgE on the IgE receptor. This binding causes degranulation. Some people's mast cells will degranulate with less stimulation than is typical. This response can be due to increased amounts of IgE on each mast cell or other genetic differences. The mediators in granules released by mast cells cause classic allergy symptoms. The type of symptoms experienced will depend on the amount of allergen and where it enters the body. Inhaled allergen will cause sneezing, congestion, airway swelling, itchy eyes, wheezing, and coughing. An eaten allergen causes swelling in the mouth and esophagus, diarrhea, and vomiting. An allergen in contact with the skin causes redness, swelling, and itching. Also, inhaled and ingested allergens can cause dizziness from low blood pressure. Low blood pressure is caused by plasma moving into the tissues and blood vessel dilation. Food allergens can sometimes enter the blood via a leaky gut. Allergens circulating in the blood will cause hives or anaphylactic shock. Anaphylactic shock is when blood pressure becomes so low that there's no longer adequate blood supply to the organs. On top of this, swelling of the upper airway obstructs breathing and further reduces oxygen. Because of this, anaphylaxis is life-threatening and sometimes fatal. The body tries to compensate for low blood pressure by increasing the heart rate. But in extreme instances, this is not enough to prevent loss of oxygen to the brain and heart. As a result, the person will become unconscious and go into cardiac arrest. Giving adrenaline via an EpiPen in the early stages of an attack can reverse these symptoms. Adrenaline relaxes the airways, constricts the blood vessels, and increases heart rate, all of which increase blood pressure. Adequate blood pressure will ensure continued oxygen supply to the organs. So, adrenaline in the early stages of anaphylaxis is life-saving. In some people, mast cells have DNA mutations. These cause them to be more reactive to known or unknown triggers. These mutations can be inherited or acquired over time. This overreactivity of mast cells is a feature of mast cell activation disorders. Examples of these are mast cell activation syndrome and systemic mastocytosis. Mast cell activation syndrome is present in up to 17% of people, which is very surprising. Unfortunately, this fact is not well known to GPs or even specialists, so people can go undiagnosed for decades. Symptoms can affect many organ systems. There can be low blood pressure, palpitations, fast heartbeat, and near fainting, flushing, hives and itching of the skin, pain in the joints, osteoporosis or osteopenia, and muscle weakness, stomach reflux, abdominal pain, bloating, alternating diarrhea, constipation, nausea and vomiting, nasal congestion, shortness of breath, localized swelling of the mouth and lips, headache, fatigue, numbness or tingling in the hands and feet, brain fog, and memory loss. These symptoms are like those experienced during anaphylactic shock.
$5 duo at Burger.
Okay, I think that's it. I don't think we need to watch Burger King. Okay, so that's all I have for you guys today. I don't want to go any further because, some people are still taking the exams. So hopefully you found that all interesting and edifying. Any questions, comments? Again, remember, no quiz this weekend. Let me look at the chat. Okay. Anything else? Nothing? Okay, I'm going to let y'all go. Last chance. Edwin. Oh,
Bye.
Thank you. Okay. All right. Bye, guys.
Bye. Have a good one.
Good luck on the exam if you haven't taken it.
Have a good one.